Okay, so it's pretty simple. But if it's well, you're gonna have to consider eccentricity all the time. Oh, it's some up here. No eccentricity, because yeah, the pin should be here. I think yes. Right here, so no eccentricity. But for this, the pin will be here, and so therefore these wells will have to consider with eccentricity because the force will be here at the pin. Okay, and for this, the eccentricity will be for the bow as well because the force is here at the pin. Okay. Now, for the single angle is a little bit problematic because the connection itself is not symmetric. So eccentricity should be considered like almost all the time, except one small case, which, you know, is not going to help us very much. But, you know, a portion of my house is a steel structure, and I use a single angle connection because I don't have that excessive reaction, right? So a single angle would be enough, and it's fine. One short calculation on one piece of paper, and then that's it. There we have it. Because the contractor doesn't know how to design it. No, the contractor. Yeah, it's a job of the contractor, isn't it? Yeah. I told the contractor, which has a good relationship with me, I'll do it myself. But the entire house has been designed by another engineer, not me. It's just good, right? I don't want to design my own house. It's going to be such a headache. Anyway, so many beams and so many levels. Who wants to do that? Anyway, let's come back here. A single plate we have to consider eccentricity on the configuration, which you will see later on. And then a T connection. T is pretty similar to the plate, but it's more complicated. I don't wish to talk about the T very much today because the connection itself is expensive and it's not very popular due to the price. But again, you may find yourself using it because it is perhaps one of the, not many options that we can use to connect the steel beam to the existing structure, such as concrete. Okay? And then the city connection, the eccentricity is empirical, but we need to consider it, yes. Now, another thing that you need to know before we get into the shear connection is that because the connection itself is for shear, so that means we need to be able to provide ductility for our beam. In other words, the beam must be able to rotate. Right? If you give the wrong detail to the beam itself would be fine. But the question is, do you consider the extra force that may occur to the connection itself? Because, if I say for the beam point of view, if you have a simple beam like this, let's say the bending moment diagram is like that. And if you provide the detail that is not really, a hinge or roller, moment will occur here. So that means the overall moment of the beam will be reduced, right? Because right here it's the same M. Correct? It's a moment envelope. So the question is, for the moment induced here by the details, do we consider our details to carry the moment? That's the question. The beam will be fine, right? If you design a shear connection and then, you calculate everything in a simple way, but then give the wrong detail and then induce a moment here. Do you consider that for the connection? And this is going to start to alter the behavior of the structure, right? Because rotation will not be like that. Okay, so that means we need to provide some ductility to our structure. This is for, a typical detail that you should not use the thickness of the plate more than 16 millimeters. And the wider the gauge, I mean the wider the distance between like these two lines, the better, because you're going to have an extra torsional stiffness, just in case the beam may twist and so on, you know. And yep, why vertical spacing? So that's the thing as well. And no weld across the top, because if you weld it like this, it has to be an L shape, so that your plate can deform and your beam can rotate. In the case like this, if you weld on top, it becomes something like what I just drew, right? It will have moment. And the question is, are we prepared this detail to carry that moment? We rather not, right? All right. The next one is the stability issue. We need to make sure that whatever we do, our structure should be stable enough. The first thing is this. Try to provide the connection deep enough, at least half of the T distance. The T distance is the distance between the two fillets, or the depth minus 2Ks, right? Remember we mentioned the K yesterday? And I think I have all the T distances included in the table behind the book as well, at the end of the book as well. So you can find the T there, and when you design the connection, make sure that sometimes if you have a long beam, you may have the small shear force to carry. Even if that's the case, the length of the connection should be half the distance of the T. Okay? And when you have the seated connection like this, you should always provide the stabilizer. This is called a stabilizer, so that your beam may not, you know, accidentally fall into sideways. But this will not be considered as a part of load transferring mechanism. We will transfer the shear through here alone. Okay, but this is provided as a special stabilizing procedure for our beam. Okay? And now what is next? Okay. Another issue that we may need to consider is the coping of the beam, because in the real construction we need to sometimes keep the level of the beam, you know, at the same, so that we can install the floor on top of it. So that means for some details, in order for it to work, you need to cope the top half of the beam out, so that the beam can be installed into the primary beam like that. So this is supposedly the secondary one, right? And if that's the case, your beam may lose some strength here because the top flange is gone. And we may need to consider the moment capacity of this small portion to make sure that it can carry the force safely to the support, because we are losing quite the significant amount of section. Okay, so by checking that, we turn this into moment by, this is your shear force, because it's a shear connection after all, right? And this shear force multiplied by the distance that it has to go from the beginning of the cope section into the end, that becomes the eccentricity. And you multiply that distance with the shear, you get the moment. Maybe I should draw something. So from that picture, we have something like this, right? You cope this, and then maybe our connection is like this. This becomes your E, right, to the face of the connection. And you have the shear here, so V multiplied by E is going to be M. Basically we check the moment capacity of this small portion, but E is not that big, so many of times we are okay. Okay. And then we will check the moment capacity of this portion from the formula shown in the slide, that is the F critical multiplied by the elastic section modulus net section, because we need to remove that, right? So you need to recalculate the moment of inertia of this section here, and then calculate the elastic section modulus, okay? And we use F critical because, ladies and gentlemen, not Fy, because right here is compression, right? We have a simple beam. So on top is compression. So that means the compression coming from the fact that this is a simple beam carrying positive moment may cause buckling to occur here. So we need to check the critical buckling stress. But again, many times you will have the large number for this. So your F critical should not go beyond Fy, okay? It's the same picture as in the handout, I suppose. Like that, okay? Here, it's a section modulus of this picture, because we're losing the top flange, right? And if it's going to be that picture if you cut both flanges. And that's a formula for F critical. I can't believe it, but the number is so big, just like that. So most of the time when you calculate this, it exceeds Fy, okay? Unless, of course, you cut it so deep, you may have a problem. So it's a straightforward calculation. And when you cut both flanges, you have another formula. And you also have two conditions: when the C is less than 2D and when C is greater than that. And generally, I have to say, if you cut both flanges, you don't have much left, ladies and gentlemen. Because we're talking about the beam becoming just a rectangular thin plate. So I used to face a situation like this, and wow, no good, sir. It just, the capacity is reduced very dramatically, and they end up having to, add the plate to the beam web to increase the capacity. Okay? And then that's it. Another issue that we have to consider. So let us now go into the details of the first connection, the most simple one, the shear end plate. It looks like that. Okay? The plate is at the end of the beam. The plate should be welded to the beam from the fabrication shop, and then brought to the site, and then you bolt the beam with the support. Should be simple, but look at the details. If the fabrication is not good, the length of the beam is not accurate, we're going to have a big problem, right? So that means the fabrication process has to be very, very good. And that means this is only popular in some places. For example, in Europe, they like it a lot. But that means that I think their quality control must be top class, because this connection is very simple in terms of behavior and design. Okay? See, that's what it is. And if you need to do the camber to counter the deflection problem of the beam, this one is no good. Can't use it, because the camber will come down to zero level after the deflection from the dead load, right? So that means you have no means to install this. So if you do pre-camber, this cannot be this type of detail cannot be used with that. Okay? See, difficult to erect. And okay, now let's go into details. So if you have this connection, what kind of failure mode do we need to check, or what kind of limit state do we need to consider? Okay, just one sip of water. Generally, this picture doesn't tell the whole story. So I need to draw it again, and you can keep that in mind. And let's come back here, because generally if you use the shear end plate, you need to cope the beam, right? So let's say this is our main beam, main girder or primary beam. And your secondary beam has to come in here like this. And then there you go, your end plate. Like that. So generally, your beam has to be coped. Otherwise, how can we use the shear end plate to install the beam to the primary one, right? So if we follow the load path, say the load somewhere, the shear will come in here. And the first thing you need to consider is the shear of the beam, just to make sure that the beam can carry shear, right? So the first here is beam shear, beam cross shear. It's the first failure that you should check, just to make sure that, okay, no mistake is made when designing the beam. And then you reach this point. So that means you need to check the cope strength, cope beam strength. Then the load travels here. Oops, it finds itself between the welding and the beam web. So the next thing we need to check is the base shear, the base metal, I'm sorry. The base metal, that is the beam web at yielding. Right? So now, this is the point where you cannot design the weld to be stronger than the beam web because of the base metal issue, right? And now, it's only normal that if you have a connection like this, you should keep it. Oops, that's a wrong line. That's the line of the plate here, right? So, if you are in the right frame of mind, you should always weld it on both sides, right? If you weld it on both sides and you have one beam web, so this becomes really the bottleneck or the weak spot of our connection. And because this is the only length that can be used to transfer the shear from the beam onto the connection, so that means when you consider the beam shear at weld, which is actually it's that one, silly me. This is always smaller than the beam cross shear, right? Because this is where the shear can fail the beam. Under this length alone, so you only need to check the load carrying capacity under shear of the beam with this length. This one will not occur before that one. Right? And then we move on, we see the weld. The next one will be, why? Weld rupture. Correct? Now you check the weld rupture, it means that you have followed the force to the weld now, to the two welds now. Now it is time for the force to start going into the plate and to where the bolts are. So when the force has reached the plate, it means that you now have to consider the big four. That is shear yielding, shear rupture, block shear, and bearing tear out of the plate itself. And after that is done, the force is now in the bolts. So we now consider the bolts, and again you now have bolt shear rupture. Right? It's exactly the same as I mentioned earlier. We follow the force because we know the load path, we know it's a shear force, and we know the failure associated with the force. And now the force has reached the beam web. This beam web, right, of the primary beam. So when the force has reached the beam web, it means that the bearing tear out of the bolt holes in the beam web must be considered. Say primary beam. Oops. Oh, off focus. Oops. All right. So you see, the calculation itself is not difficult. You know the core strength from that formula. This is the most complicated one with that formula. And then you calculate the base method. That is, of course, 0.6 Fy multiplied by the web thickness multiplied by this length. And then you calculate the well strength. It's, of course, that 0.6 Fexx multiplied by 0.707 multiplied by the size of the well, and then multiplied by L. And then the big four, shear yielding, shear rupture, 0.6 Fy multiplied by this length, and then multiplied by the thickness of the plate. Keep in mind that the shear yielding and shear rupture should occur on both sides, right? So you have two planes in this case. And then the block shear, for the block shear to occur, is this piece. Let me draw a bigger picture. For the block shear to occur and for the connection to fall down, this is where the block shear is going to occur, right? And then you have the bearing tear out of these four holes, which, this is the LC of that bolt hole, and that is the LC of the internal bolt hole, right? So it's not that the calculation itself is not difficult. You just need to know what to check. That's all. See, it's all about dimension. It's either the strength multiplied by this and multiplied by that. So if you can get the right dimension like this, it's a piece of cake. And let me complete this by drawing the side view of the primary beam to show you the bearing tear out. So if this is a primary beam, you will see the bolt holes like this, right? And this becomes the LC. If the beam is going to fall down, it means the tear out should occur down here, right? And what about these holes? The tear out should not occur here, because it's impossible for the tear out to occur through the beam flange. So that means these two holes on the edge, you should only consider bearing failure. Right? So it makes sense. Not that difficult. Okay? And that's it. Shear end plate is done. Now you know how to take care of one connection, one shear connection. What else do you want to know? That's it. Right? How many minutes do we have left? Oh, we have like almost 10 minutes. Okay. I think I can still hang on. I need to go to the toilet. That's fine. All right, so we're back here. Now, any question with the shear end plate? That can only mean crystal clear, right? It can only be one way. So now we move on to the double angle. Okay, this shall be the last connection before lunch. Okay, and then we try to come back and finish everything. Don't worry, we only have like 40 slides left after lunch, so we could just wrap it up very quickly. Okay, now as we suggested, this is the biggest connection, shear connection available because you have two angles. So that means when you consider this, you always have two plates on both sides. So it should be able to handle the connection up to 200 tons or so or more. Okay? And very adjustable and can be used in association with the moment connection. That means you can use this detail to transfer the shear in the beam web, and then you can connect both flanges with another detail to transfer moment. Okay? And not the safest one or the most economical one because it is big. And sometimes, if you can, we attach the angle to the beam and then bring it to the side and then connect the beam and the angles to the support. Okay, all right. We have 3 combinations for this. I don't know why I began with this, but can we just skip this to? This is called the welded bolted. That means I weld my angles to the beam and then I will bring it to the side and then bolt them, bolted, one beam, right? Bolted to the support. So this is called the welded bolted. Okay, that means when you want to consider this, what do you need to do? The next picture is better. This is really, we weld the angle to the beam, the 2 angles to the beam, and then bring this portion to the side and then bolt the 2 angles to the support. Okay, so what do we need to consider this? Now, drawing a picture does help when we talk about the load path, Again, when you have this, it means that if we cope the beam, because we need to bring it into the primary beam, so it looks like this. Okay. Now remember, this is on the beam side, so you could actually weld it like this. With the C shape, you can weld on top because the rotation will occur where the bolts are, which is here, right? So now again, we'll follow the load. So the first would be to make sure that the beam is okay, so we check the beam shear. And then the load will come to this section where we need to check the cope section, right? Cope strength. And then we're here. Again, we check the base metal. Or the beam web itself. Should be here. Beam web strength. Now this again, you have welds on both sides because you have 2 angles, and you have 1 beam web which can be very thin, so it can again become the weak spot of our detail. But one thing extra that may occur with this detail is this. Because we will it like this, and because we have the cope section, so this piece, ladies and gentlemen, can be sheared off, this beam web, and that becomes a block shear failure. Right? This, the piece of the beam web behind this well line can be sheared off. So that is the block shear failure. Okay? Oh. Many people would love to use pink, right? That's why it runs out. Use the blood red. Oops, block, not black. Block shear. Beam web, right? And then it's now time for us to move the load to the well. So now it's a well rupture with eccentricity. And the eccentricity would be the distance equal to the distance from the centroid of the well to this face, right? Because that's where the shear is. It's not that difficult, is it? And after you're done with this, now, if you have the manual, you can just look at the table. They have this kind of information. If you don't, a classical should be fine, right? And after you're done with this, it means we will follow the load into the plate. The angles, I mean. And that would mean big 4. And that would mean bolt shear rupture and that would mean on the support side, let's use another color, right? It's kind of getting more fun now. Ooh, here. And then the bolt holes on the support side. Oh, it's not very clear. I really want to use orange. Blue is fine. And then the bearing tear out on the support. So, voila. Another detail is done. That's simple, right? See, it's not that difficult as long as you know what to do. And that is 11:30 right on the mark. I should have like half an hour left for the next session with 40 slides. Ooh, less than a minute per slide. I know, I've seen him. No mistaken identity. That is the real Ajahn Sutat nakrab behind you. Any question, ladies and gentlemen, before we have lunch? I really need to go to the toilet. Too much water. Yes. Well, the block shear may be less than the beam shear itself. All right. Well, because the base material would be concerned with this shape, right? But then when the block shear failure occurs, you will have this. But yeah, it's going to be close. I see where you're coming from. Where's the pink one? The pink one is gone, right? So yeah, when the block shear failure occurs, it's this part. So it's not really the same one. It's going to be closed. Maybe it depends on the length here. Maybe the block shear is less because this length is shorter than that, right? So the block shear itself may occur before the fail of the base metal. Shorter. And the beam web is not very thick in general. So it can fail like that even before the failure of the base metal underneath here because you generally have a longer length, right? It's a good question. Yes. Let's have lunch.